All right, so this is our last week of class. Lots of stuff to go through, but you know we've basically covered everything that I was hoping we would cover this quarter. But I want to spend some time today talking more about Verilog. I want to go over the homework. I want to talk a little bit about the lab. I want to look at the traffic light in terms of Verilog implementation and maybe simulate that with the LDEC software you've been using. I want to touch on a few things from Chapter 9, including how we do subtraction, make a few comments about that, show you some applications of multiplexers, and whatever else we want to talk about. And then Thursday we'll probably spend just, you know, kind of quick review of the whole course and any final questions that you have, and we'll talk about logistics for the final exam. Let me mention something up front. So there's emails going around about an action to shut down STEM on Wednesday, and it's part of you know, an organized effort to raise awareness to some of the issues that we're hearing a lot more about today, racial injustice and so on. I absolutely support these efforts. I absolutely believe that you know, we need to move to a place where everybody is treated equally and respectfully and so on. But I don't think that the last week of classes is an opportune time for me to express that support by boycotting my STEM-related activities for a day. So I am planning to have my classes as usual. I will have my 2 office hours tomorrow as usual. Okay. We don't have class Wednesday, so that doesn't affect anyone as far as attending or not attending. But I will have office hours at 11 o'clock and then again at 3 o'clock tomorrow. And again, it's not that I don't support efforts to, you know, take action in the name of trying to bring about equity, but I think education is an important key towards improving this horrible situation that we're in. I mean, we've been dealing with this for a long time, and I honestly think things are getting worse right now, not better. And I think the way out of this is education. I think it's up to, you know, the people who are going to be the next generation of leaders have got to bring something different to the equation, and I think education is a big part of that. So anyway, I'm not going to get all soapboxy, but I support this effort, but I'm still going to be doing teaching and office hours tomorrow. All right, so any questions before we get into you know, going over the homework in the lab and stuff like that? Any general questions or specific questions or things that you definitely want to go over that we can go over first?
Since we submitted the lab reports and all that whatnot, could we be able to go like thoroughly through all of the experiments? Because my LDEC server just kept on crashing. I don't know from what reason, and wasn't able to complete it to the best of my ability.
Mm-hmm.
So,
in what way was your server crashing?
I mean, it just kept on just crashing and logging out. So right now I'm using a Mac computer, and I tried to install a Windows platform into it, but
So
I don't know.
So it's doing similar things to what mine is doing, which is running on a Linux platform. Yeah, the software does not seem to work terribly well under emulators like that. Unfortunately, you know, if this had come up earlier, right, I have other types of software that do work well under Mac and under Linux that we could talk about, but not, you know, in the 11th hour, unfortunately. But there are a lot of packages out there for doing Verilog and for simulating it. So the one that I have used in this class before is something called Icarus Verilog. And I'm pretty sure they support Mac. They definitely support Linux. And it's not as much of an integrated environment where you can just sort of drag and drop. And you have to get into talking about what are called test benches, which are actually discussed in some of the documentation that I've posted. But it lets you, write Verilog, compile it, and then simulate it and look at waveforms. It's just a little less intuitive than the LDEC tool, but does work on other platforms well. So yeah, we will go through those examples. Not everybody has turned in Lab 7 yet, right? Because labs are the one thing that can be turned in late. So I don't want to flesh out all of those details, but we can definitely go through, representative implementations. But I also want to go through the homework in a fair amount of detail, and it's basically the same process between the homework and the lab. It's just different particular things that you're trying to build. So so we'll definitely go through that, and then Thursday we can go into bigger details. Anything that you want to turn in late, which is really just labs, I want by the beginning of class on Thursday. Okay, that's the last chance to reasonably get stuff in and get it graded. So beginning of class Thursday. All right. What else?
Could we be able to go over the different kinds of errors and syntax errors and how could we fix them? Because that was one of the parts where I usually get stuck and I wouldn't really know how to fix it.
Yeah, and again, the best solution for that is to come to office hours or send me an email with a screenshot or something. But usually, come to office hours, screen share, and we'll figure it out. And we can look at some of those. But it's really hard. I get a note from somebody the day before an assignment is due, and they say, "I've spent 16 hours online looking for an answer to this, and I can't find it." Don't spend 16 hours looking online for this, right? Get in touch with me, come to my office hours and say, "Hey, here's my code, here's the error I'm getting, what do I do?" And we'll figure it out. And it's usually really, really simple, but that doesn't mean it's easy to find, right? It's usually there's a missing semicolon or there's a missing end statement or something like that. The software is not incredibly good at helping you figure those things out, okay? But I've made so many syntax errors in my life that I'm pretty good at spotting them now. Okay, so particularly if you've got the code in front of you and I'm looking at it and we can say, try this, try that, we can usually make pretty quick work of it. And the more that you get experience with spotting and correcting these errors, the quicker you'll get at it, right? So I'll go through some of them, but I don't really have, a list of all the different types of things that can go wrong or the different messages you can get. But we'll look at some examples and see if that helps. But again, if you can hop into office hours, share your screen, show me exactly what you're doing, we can try to figure it out from there. Let me fire up this code. So some people had code like this, and end module is getting underlined, right? And you try to compile, and it says, syntax error, unexpected token, end module, and you click on that, and it brings you right here. But there's nothing wrong with the word end module, okay? And if you look at the previous line, what does it say? Begin ... end pair mismatch detected. One end token are missing. Right? What it's really complaining about is the fact that right here we said begin and we didn't have a matching end. And it knows that because we got to the word end module. But the problem is really right here. It wants to see an end. Probably with a semicolon. So put that in and compile. And that points out a second problem, right, which is undeclared identifier clock CLK. Well, I said clock, but remember, Verilog is case sensitive. So uppercase C, lowercase lk is different from all uppercase CLK. So fix that. Recompile. The way to fix it was put end module on the very, very last line. Yeah, having extra things after an end module will sometimes cause it confusion too. Alright, so I got rid of the error about clock. Now I've got another error message here. And it says count is not a valid left-hand side of a procedural assignment. Well, that doesn't really tell us a whole lot, but remember, in an always block, what we're doing is we're saying when this event occurs, I want this to happen. I want count to be set equal to this expression. Well, if count is a wire, we can't say I want you to take on this value and remember this value. It has to be a register. So up here I need to say something like register count. And now try to compile. And finally it compiles. Okay, the last thing I would do is I would make this a non-blocking assignment, because I always want you to do non-blocking assignments unless you really have a reason to do a blocking, but it compiles either way. So that's a variety of different types of errors that can show up, you know, maybe close to where it's saying there's an error, maybe not. Here's another one. Right, that's an easy one to make. Here's another one. Right, so this is giving us a warning, and the warning is because we have something after the end module statement. In this case, we have a semicolon. So get rid of that and recompile. And we're back to success. So by the way, on my version of the ALDEC tool, I've somewhat localized at least some of the things that make it crash. One thing that's almost guaranteed to make it crash, and I do this all the time, I want to select a set of text. I'll do Control Shift and a back arrow key. That's going to bring it down. I don't know why, but that almost always is guaranteed to crash my version of it. So I've just, you know, had to rehab myself to not do that when I want to select a bunch of text. I was wondering if anybody was experiencing the end module error when creating any Verilog. Yeah, that's what I was just talking about. Actually, it was in response to your lab report. And the punchline was it's not really an error with the end module. It's an error with, you know, among other things, not having the end keyword there. So when you compile, it says there's something wrong with end module. Well, it's something before that that's actually the cause of the problem. But again, if you can screen share and we can work on it, you know, in real time, that's usually pretty effective for tracking these things down. But Verilog is kind of notoriously picky, right? I mean, it's not picky. It's very clear about what it wants, but it's very specific about what it wants, and it can be challenging to find that sometimes. All right, well, let's look at the homework. So write Verilog code to implement the function f equals all of this stuff. So I don't know, let's make A, B, C, and F our ports. We'll make those wires. We'll make F an output. And so this is a different function because I don't want to do exactly the function that's given on the homework, but just to give us an idea. Will Verilog be on the final exam? Yeah, definitely. Which is why it's worth spending, you know, the next hour and 50 minutes talking more about Verilog. Because yeah, Verilog will be on there. So did that really compile with no errors? That's hard to believe. Okay. So so simulation. So a lot of people had trouble with simulation on the homework. I said, you know, that's fine. On the lab, you were required to do the simulation in addition to the actual Verilog. And a lot of people had trouble with this, right? So again, it's in the videos, it's in that write-up on Canvas, but a number of people who weren't able to get this to work were able to come into office hours and then share their screen and then go through the steps, and we could pin down exactly what was going wrong and get them back on track. So there are a number of ways to do the simulation, okay? I know one way, and I've only talked about one way, and so every time that I do this, it should be exactly the same set of steps, okay? And if anything goes slightly different from this, you want to close everything out and start over, okay? Because, you know, you're supposed to hit an X and you accidentally hit a Y. Going back and hitting an X is not necessarily going to be the same thing as just hitting the X, right? Particularly with these integrated environments, right? Everything has an effect. So if you're supposed to initialize a simulation and you accidentally say restart the simulation, close everything out, go back to the beginning, start again. Okay? It's a bit of a pain, but you want to learn the sequence of steps that works for you. And the best way to do that is to have one sequence of steps that's going to work. So here's the sequence I'm suggesting to do simulations. We've compiled our design, and we got no messages, okay? First of all, make sure in the very beginning, it says this in the lab, we said this in class, before you do anything, one time, you have to set up your properties. You have to go under Tools, Preferences, Simulation, and where is the design window? I could go back and read it from the lab. Under Simulation, Access to Design Objects. By default, this box is checked. If you try to simulate and it gives you errors about forcing values or something like that, it means you did not do this one-time setup. So you come in here, you come to your Preferences, expand Simulation, come down to Access to Design Objects, uncheck this box and check these three boxes. The reason for doing that is to tell the simulator that you are allowed to set the values of signals. Otherwise, it's not going to let you. Okay? Say apply, say OK. That's only once after you install the software. Shouldn't have to do it again. Alright, so put in your Verilog, compile it, make sure you got 0 errors, 0 warnings, and then do File, New, Waveform. Okay, one thing that won't be on the final, I won't ask you to do stuff with the LDEC software. Okay, so I'm not going to ask you what should you click after you do such and such. Okay, but I will ask you about Verilog and writing Verilog and analyzing Verilog itself. Alright, so file, new waveform, and then simulation initialize, and it should bring up this window. If it doesn't, there's a good chance you've done something else already, in which case close everything out, start over again. Okay, but it should bring up this window which says select top level design unit. Say OK, expand your module name, click on the bottom entry which is your design name with a little green symbol with a gold star on it. Say apply, say OK, and now you should have this window over here on the left with all of your variable names, and then a signal window in the middle, and then your timing diagram area on the right. So you can drag these over one at a time, or you can just drag this symbol on the top. And then you set up your stimulators. So I've got 3 inputs. I'm just going to go ahead and use some clocks. So I'll say let's put a clock on here that's 10 nanosecond period. And here you have to say apply. And then B, I'll set up a stimulator and let's do a 20 nanosecond and apply. And then C, I'll set up a stimulator and let's do that at 40 nanoseconds. So I'm going to try to get every possible combination of these signals. And I'll go back and double check. This is 20, this is 10, this is 40. And I applied it. And so now I can say run the simulation for 100 nanoseconds, and we can see different values of the inputs, and for each of those the corresponding value of the output. Alright, and I used a different function from the one in the homework, but in the homework it's, you know, not A ANDed with B ANDed with not C, or not A ANDed with not B ANDed with C, or A ANDed with not B. And so just put in the appropriate equation and you're good to go. Alright, question 2, Verilog to implement a positive edge triggered T-latch. Okay, so this was the question that I graded, although I looked at the other ones and wiggled the grade around a little if you did other things well. So what does a T-latch do? So there's an input T, there's an output Q, there's a clock. And it's edge triggered. And it said positive edge triggered, so it's on the rising edge of the clock that things happen. And the behavior looks like this. If T is a 0, the output doesn't change. If T is a 1, the output toggles. Alright, so T is a 0, the output is stable. T is a 1, the output toggles. So here's something that I do when I'm writing Verilog and I haven't written it in a while. Find some Verilog code. So I don't remember which one of these I posted on Canvas, but I think it was this. Okay, it's easier for me to start with existing code to figure out the syntax. For example, I don't need a semicolon after begin. I do need a semicolon here. I don't need it after end. All of that stuff, right? That that isn't necessarily committed to memory. So how am I going to code this up? I'm going to do an always block, and I'm going to go at the positive edge of clock. And I'm going to basically say if T equals 1, then I want Q to be the complement of Q. If T is 0, I don't have to do anything. Okay, because when the T input is 0 and the clock ticks, the output doesn't change. The only time anything happens is when the clock is ticking and your T input at that moment is 1, then we should toggle the clock. Okay, so for a D flip-flop, right, the output was just set Q equal to D. For a T, it's going to be, if T is equal to 1, set Q equal to not Q. Okay, so now we have inputs which are a clock and a T, and we have an output which is Q. And let's just go ahead and do a Q bar output as a bonus. So clock and T will be wires. Q will be a register. Q and Q bar will be outputs. Clock and T will be inputs. And Q is going to be register. So at the positive edge of the clock, begin, and if T equals 1, Q becomes not Q. And end. So let's just try this, and then we'll add in Q bar. Let's see if this compiles. It compiles. I'm going to close out this simulation window. Yeah, I'm going against everything I just told you, which was like always do things exactly the same way, but I'm trying to be lazy. So I'm going against my own advice. But let's see what happens. Let's drag this stuff in here, and I'm going to set up my clock to be a clock, and 40 nanoseconds is probably a good clock rate. And let's set our T signal to a different kind of clock. Let's set it to 103 nanoseconds. And so one thing you'll find when you play with Verilog is sometimes, you've got all your Verilog code written, it all looks good, but your output is undefined, right? It's this X value here, which is saying it doesn't know if the output is high or low. And if you go back to your Verilog and you look at what you've actually said, we've said, in some cases Q should become the opposite of the current value of Q. But the poor simulator doesn't know what the current value of Q is. We haven't told it, and so it can't, figure out what the complement of it is because it doesn't know the value of Q. Okay, this is the problem in the lab. If you take a flip-flop and you put power on it and you look at the output, are you going to see a 1 or a 0? I don't know. You'll see either a 1 or a 0. It's not going to be undefined, but we can't really predict what it's going to be until we actually hook it up. And the simulator simply throws its hands up in the air and says, well, I don't know if it's a 1 or a 0. So it shows us this trace which has both a high and a low line on it. All right? So one way to deal with this is go ahead and add a reset signal. So let's put a reset in the beginning. Let's make it an input. Let's make it a wire. And now let's modify our if statement. So at the positive edge of the clock, we'll say if reset equals 1, Q goes to a 0. else if t is equal to 1, q goes to not q. Yeah, me too, actually, when I first learned this stuff. The reset is pretty key. And it's usually something you want actually in physical systems too, because occasionally it's possible that you have a state machine that you've carefully defined, but there's some particular condition you hadn't considered. Like maybe we have 6 possible states, but it turns out if it happens to come up in one of those other 2 states, it might get locked into those and not be able to get to a state that we actually want it in. So we usually want some kind of reset in our design. It's really weird that this is all compiling without errors, because I'm kind of making this up as we go. Okay, so let's go back to the simulation. Let's end the simulation. Let's just close this out. Let's do a new waveform. And I'm doing a new waveform because I have different signals now. Right? I have a I should have a reset. Alright. So I'm getting a lot of signals now, so I'm just dragging this thing over, which automatically gives me all of my signals. So let's go back, let's make our clock. That's 40 nanoseconds, and our toggle line is 103 nanoseconds, so I'll stick with those. Let's go ahead and do something with the reset. So I'm going to set this up with a formula, which is going to say, let's start off at a 0 at 0 nanoseconds. Let's raise to a 1. Actually, let's just start at a 1 at 0 nanoseconds, and let's go back to a 0 after 10 nanoseconds. Alright, so this is saying my reset should start off high and then it should drop down low. My clock is just going to be toggling every, let's do this every 20 nanoseconds. We'll have a pretty fast clock. And then my toggle input is going to change slowly. Roughly every 5 clock ticks, my T input will go high. Alright, so I'm going to put my clock up top. And I'm going to put my reset all the way up there, because I'm not too worried about my reset, and I want to mainly look at Q, the output. Okay, so let's run this. And apparently nothing is happening, right? Does anybody see why? It's kind of subtle. So my reset is what we call a synchronous reset. It's saying this reset takes effect when the clock ticks. So it's not enough to just raise the reset line for a few nanoseconds. The reset line has to be 1 when the clock ticks. And unfortunately, I chose to pull the reset line low at 10 nanoseconds, which is when the first clock tick occurs. So when the clock actually ticks, this reset is already 0, so it doesn't do this reset statement. So I'm just going to change my stimulator on reset, which was a formula, and I'm going to say, let's go down to 0 after 15 nanoseconds. So the reset line will still be high on that first clock tick right here. And now I'm going to say end simulation, and let's go ahead and run the simulation. And so now we can, I'm going to use control scroll wheel to zoom out a bit. Now we can see what's happening. Okay, our reset line was active here, and so on the first clock tick our output went low. That's what the reset does. and then the reset came down low. So where are the positive clock ticks? Right here, and at this point t was 0, so nothing happened. And at this point t was 0, and so nothing happened. But on the next positive clock edge, which is right here, t is a 1, the output toggles. And then the next positive clock edge is right here, and t is still a 1, so the output toggles again. And then the next positive clock edge is right here, and at that point t is 0, so the output stays at its current value. So that's a good T flip-flop. Alright, what about Q bar? So I could say, you know, if reset equals 1, set Q equal to 0 and Q bar equal to 1. Otherwise, if T equals 1, set Q equal to not Q, set Q bar equal to not Q bar. That's more code than I want to write. What I'm going to actually do is I'm going to make Q bar a wire, and I'm going to build a piece of combinational circuitry. I'm going to say assign Q bar equal to not Q. In other words, I've got all of this Verilog already, which sets up Q correctly. This statement here is just going to say, let's take the value of Q, run it through an inverter, and feed the output to Q bar. And it's outside of my always block, so I can use the assign statement. And I'm basically just generating this complemented Q signal. So we can compile that, we can go into our simulation, we can say restart. And now you can see that Q bar is nicely the exact complement of Q. So if you want to practice Verilog, right, it's a whole lot more rewarding to practice it when you have access to a simulation tool than to just kind of write Verilog and hope that it's right. So it's worth using this software, you know, or some other piece of software to be able to simulate your designs. Okay, so that you can see what the code's actually doing. All right, let's see what else we got. You know, a positive edge triggered SR flip flop. Well, it's going to be pretty much the same as the JK flip flop, except it doesn't toggle when both inputs are 1. So let's see. Question: can you not simulate with other software? Yeah, you can. Icarus Verilog comes with something called GTK waveform, and that's something you can use to view timing diagrams. The SR flip-flop was confusing. So let's finish up with the T. Actually, let's say something more about this, right? So I wrote this behaviorally, right, saying if T is 1, let's toggle Q. That's what a T flip-flop does. But there's other ways we can get the same effect, right? One way to look at this is to make a table like this. And say if T is 0, we're not supposed to change Q. So if T is 0 and Q is 0, the new value of Q is 0. If we're not toggling and Q is 1, the new value is 1. If we are toggling and Q is 0, it should become a 1. And if we are toggling and Q is currently a 1, it should become a 0. And so the new Q looks like just the exclusive OR of the toggle input and the old Q, or the current Q. And so you can write the statement as just Q is T XOR Q, right? And that's a trick, but to me it doesn't come as naturally from understanding T flip-flops as something like this, which says if T is 1, toggle the value of Q, right? So this gives you an equivalent circuit. It probably synthesizes to exactly the same circuitry inside, but it's a little obfuscated. I can't say that word. It feels a little less direct to me. Okay, and that's a bit what's going on with the JK flip-flop solution. So let's look at a JK flip-flop. So we can think of this as a function of 3 variables. As follows. If J and K are both 0, we should not change the flip-flop's value, so the new Q will be the same as the old Q. If J and K are 0, 1, the flip-flop should get reset. If J and K are 1, 0, the flip-flop should get set. And if J and K are both 1, the flip-flop should toggle its output. And so we could write an equation for the new value of Q in terms of J, K, and the old value of Q. So let's fill in a K map. 0, 1, 0, 0, 1, 1, 1, 0. I did not do that right at all. I'm not even going to try to erase it. I'm just going to redraw it. Let's try it like that. Alright, so we'll set it up like this. So this is a 0, that's a 1, that's a 0, that's a 0. And then this is a 1, 1, 1, and a 0. So Q plus comes from this rectangle, which is K bar Q, comes from this rectangle, which is J K bar, and it comes from this rectangle, which is J Q bar. I'm way off my game here. We didn't need to do this rectangle. So it's this rectangle, which is K bar Q, and then just this split rectangle, which is J Q bar. Okay, and that's the equation we have in the solution here. J ended with Q bar, or K bar ended with Q. Okay, so that is a solution. Yes, you're right, I didn't need that middle term. This is a solution, but to me it's not as intuitive as saying, you know, if J equals 0 and K equals 0, don't do anything. If J is 0 and K is 1, set Q to 0. If J is 1 and K is 0, set Q to 1. If J is 1 and K is 1, set Q to not Q. So 4 if-then statement, or 3 if-then statements, right, captures the behavior of this, but we can write it more succinctly by using this one assignment statement, right? But this you have to kind of reverse engineer to figure out that what's going on is we've written a truth table for the new value of K in terms of the current value and the JK inputs, right? This is something like the excitation table written in reverse. But we could do it with a series of if-then statements like this. Okay, so for the SR flip-flop, we can do the same thing, except it's not clear what the SR should do if both inputs are 1. We could decide to do nothing, or we could decide to, make the set take priority. In some cases, if S and R are both 1, then both Q and Q bar will be set to 1. And it depends what you define, but I would make a transition table for the SR latch that you're implementing, the flip-flop you're implementing, and say, here's the behavior, and then write the Verilog code for it. Does that make sense? Alright, 4-bit up counter, there's a solution for it. 4-bit down counter, just subtract 1. And we don't actually need to do all of this business. If we have a 4-bit register and it's equal to 0 and we subtract 1 from it, it's going to go to 1111. Alright, so really all we need here is count equals count minus 1. And it'll automatically roll over because it has no other choice. Right, 0 minus 1 is 15 if you live in a 4-bit world. And here, by the way, we're avoiding having a reset by initializing the value of this register to, in this case, 4 zeros. And this will work well when we simulate, but it creates something that we call non-synthesizable code, perhaps, right? It may be that the circuit you're building will not exhibit this behavior. It will not automatically be initialized to 0 when you power up, right? Because that's a hard thing to do, to build a flip-flop that starts off at a particular value. A reset input will create synthesizable hardware, and it will probably build a circuit where your flip-flops have something like a reset input, which is fed by your external signal. And if I code that reset to be synchronous, if I put it inside an always block, it will use a flip-flop that has a synchronous reset. If I did it asynchronously, it would make something that simply goes to 0 as soon as that input is asserted, whether the clock is ticking or not. Alright, let's talk about decoders. Decoders and encoders, and then we'll take a break, and then we'll talk about traffic lights. A 3 to 8 line decoder, active high. So the idea here is we want 3 select lines, 8 output lines, which I'll call Y0 through Y7, and we want one of these lines to be high based on the input going into the select. So if we made this, a single 3-bit register called S, we could say something like if S is equal to 0.
Professor, if you're writing something down.
Thank you. Appreciate it. All right, so a 3 to 8 selector, right? So 3 input lines, which we can think of as S2, S1, S0. We could think of that as a 3-bit register called S. And we want to set one of these outputs high and leave all the others low based on the value of S. So if S is equal to 0, we want 0 to be equal to 1, and Y1, Y2, and Y7 to be equal to 0. If S is equal to 1, then we want Y0 equal to 0, Y1 equal to 1, and Y2 through Y7 equal to 0. So function table. And I can write sloppy because it'll be clear in a second. So 8 possible input values. Basically, these select lines choose which of these output lines is supposed to be high. Right? And all the other lines are 0. So exactly one of these lines is asserted. And since it says this is an active high, asserted means turn to a 1. So we can do this with a series of assignment statements. We could say assign y0 equals s equals 0, 1:0. So if s is equal to 0, y0 will be high, otherwise y0 will be low. Assign y1 equals, well, if s is equal to 1, y1 will be high, otherwise y1 will be low. Assign y5 equal to, well, if s is equal to 5, set y5 equal to a 1, otherwise set it to a 0, and so on. So 8 assignment statements will be the bulk of your Verilog. And then it's just define your inputs, S0, 1, 2, define your outputs, Y0 through Y7. I could instead define my output to be a register containing 8 bits. And instead of saying Y5, I could say Y bracket 5. And instead of Y0, I could say Y bracket 0. And so on. Or I could call my outputs A, B, C, D, E, F, G, H. Whatever I want. So that's a decoder, right? It's taking a small number of bits and using it to drive a larger number of lines. The other direction is an encoder. So 8 to 3 encoder. And it's saying active low. And there's different types of encoders, and we haven't really talked about a whole lot of them. The most common one you'll find is called a priority encoder. But the solution that most people turned in was for just a plain old generic encoder. So the idea of an encoder is basically you have 8 inputs. So input 7, 6, 5. And active low means, well, we're expecting exactly one of these 8 inputs to be active. So it could be that input 0 is active. It could be that input 1 is active, right, meaning it's low. It could be that input 2 is active. And so on. And there's 4 more rows down here. And your output, Y, should tell you which bit number is active, which input is active. In this case, input 0 is active, your output should be 0. In the second row, input 1 is active, your output should be 1. Third row, input 2 is active, your output should be 2. Here, input 3 is active, your output should be 3, and so on. Right? These are the inputs, these are the outputs. But it's basically the opposite of what a decoder was doing for us. It just goes in the opposite direction. So how do you do this? Well, you can do it with a few assignment statements. So let me go ahead and fill out the rest of this. All right, so how do we describe y0? Well, y0 should be asserted if either input 1 is 0, or input 3 is 0, or input 5 is 0, or input 7 is 0. So assign y0 equals, so not I1, or not I3, or not I5, or not I7, question mark. So if any of these are true, y0 should be equal to 1, otherwise make it equal to 0. Okay, y1 should be true in these 4 cases, which is when either I2 is a 0, or I3 is a 0, or I6 is a 0, or I7 is a 0. And then similarly for y2. If I4, 5, 6, or 7 are zeros, then we want y2 to be a 1, otherwise it's a 0. So those are both combinational circuits. We don't need any clocking, we don't need a reset, we don't need an always block. It's a bunch of assignment statements. And this will synthesize to, you know, sum of products or product of sums or something that, you know, is the same thing we would come up with if we took this and you know, made a K-map and simplified it and so on and so forth. Okay, it's a pure combinational circuit. All right, so let's do a 5-minute break and then let's look at the traffic signal, because the traffic signal is pretty fun to mess with. So a 5-minute break, we'll come back and play around with that.